When a highly engineered material under stress finally shatters, examining the broken pieces by eye won't tell you why it failed. A surface-level inspection can only show you where the break happened, not the microscopic weakness that caused it. To understand the root cause of a failure, material scientists have to look much deeper. They have to interrogate the material down at the quantum level. Their primary tool for this interrogation is the X-ray. X-rays operate with a unique dual nature, behaving as continuous waves of electromagnetic energy, but also as discrete packets of particles, or photons. This chart quantifies that duality. Equation 4 establishes the mathematical link between these states, showing an X-ray photon's energy is inversely proportional to its wavelength. By substituting known constants for Planck's constant and the speed of light, we get 12.398, allowing calculation of either property. Controlling that energy and measuring how these quantum particles interact with a physical sample forms the foundation of materials characterization. The mechanical process starts inside an X-ray tube by taking a target material and bombarding it with a continuous beam of high-energy electrons. As those incoming electrons plow into the dense atomic structure of the target, they undergo a rapid, violent deceleration. Looking at this diagram, we see the primary electron slowing down and changing direction as it passes the nucleus. Because energy must be conserved, this sudden loss of momentum is released as an X-ray photon, a phenomenon known as bremsstrahlung, or braking radiation. When we plot this radiation on a detector, it doesn't give us a single crisp point. Instead, it creates a broad, continuous curve of varying energy levels. This continuous spectrum gives us a solid baseline of physical data. But because it spans such a wide band of radiation, it is not specific enough to let scientists identify the exact chemical elements hiding inside a material. This graphic details a specific collision. An incoming electron ejects a tightly bound electron from the inner K-shell. Instantly, a higher energy electron from an outer orbit drops to fill the gap. It sheds excess energy, represented by these wavy lines, creating a characteristic X-ray. This chart shows how those specific emissions appear on our data readout. Instead of a smooth hill, they punch right through the broad braking radiation curve as sharp, intense peaks, specifically labeled here as K-alpha and K-beta. This table outlines how the target anode material inside the X-ray tube must be carefully selected to control these outputs. Materials like chromium, copper, or molybdenum generate different characteristic wavelengths, which helps optimize the beam and prevent unwanted fluorescence. Because every element on the periodic table has a totally unique electron shell configuration, the distance those electrons drop will always be identical for a given element. These sharp, characteristic peaks appear at energy levels specific only to that atom, allowing us to identify the material's composition with absolute certainty. This flowchart illustrates how that exact same physics principle, measuring how atoms absorb and emit X-rays, is deployed across a variety of specialized laboratory techniques to determine structure, composition, and electronic properties. Here we see an interface for SEM-EDX analysis. By plotting exactly how often specific characteristic X-rays are received, this technique can calculate the exact percentage composition of elements in a sample while simultaneously mapping its physical topography. This schematic demonstrates X-ray fluorescence, or XRF. By firing an incident X-ray into a bulk sample and counting the resulting characteristic emissions, scientists can rapidly quantify the elements present throughout the bulk of the material. And these graphs show the output of XPS, or X-ray photoelectron spectroscopy, performed on carbon nanotubes. Instead of measuring the emitted photons, XPS measures the electrons kicked out of the top 10 nanometers of a material, providing highly sensitive readouts of its surface chemistry. By controlling the generation of X-rays and carefully analyzing the precise peaks they produce, material scientists can reverse engineer these invisible atomic behaviors into the hard, macroscopic data required to drive modern engineering.